Today we are going to do section 7.3, polar coordinates. Now you likely have done some of this in the past, but in case you haven't or in case we have forgotten, let's do a quick review of what it is. And what it is polar coordinates are a redefinition of the, what is this called? The regular rectangular coordinates. That is, what you're going to do is you're going to define x as equal to, but first let me draw the graph. Now here's a point xy, okay, where we normally have it, and any point like that is going to make an angle with the x-axis, right? And that's called theta. And then there's a length to this thing, and the length here is r. Now what we're going to do is define it as with trigonometry. That is, x would, just based on this graph, x will be equal to r cosine theta, and then y will be equal to r sine theta. Right? This is the sine theta, and that's the cosine theta, and so on. Now, just based on that fact alone, we come up with something called the polar coordinates. That is, instead of representing a point as xy, now we're going to represent the same point as r theta. Like this, where in the relationship is defined this way, okay? Where r equals to, well, you're going to figure out what it is in correspondence to that, where r is, where x is our cosine theta and y is our sine theta. Actually, it's not written this way. I shouldn't say this. But the point is, what I should say, let's stick with the book says. So such that the cosine theta is defined as x over r and what? Well, and x equal r cosine theta. And then sine theta is equal to y over r. And then there's another where in this situation, then r squared is equal to x squared plus y squared by the Pythagoras theorem. And then theta has this relationship where tangent theta, okay, is equal to y over x. So all these relationships are spelled out, and that is the definition of the polar coordinates. So then, as you can see, you can, any point that's x, y, you can pop it into the polar coordinate. And we will do that in a second. But first, let's look at the next page. Well, the next page repeats that, and let's look at example 7.10. That is, for example, 7.10 part A, example 7.10, on the following page, where we have, if you have x equal to 1, y equal to 1, what is the corresponding polar coordinate? Where r equals to, you plug it into this formula. Where's my formula? Well, whatever. You just plug it in, some r equals to this, okay? And then theta equals to this. So you plug it in, and then out pops your value for r and theta. Now, as you can see, let's look at example 7.10 for a second. Now, if you plug into the, let my book focus here. Okay, if you plug in the value, then you get some value for r and theta. But as you can remember, r and theta are not unique. For example, you can have, for the negative value of r can also satisfy this problem. But for now, let's not worry about that. Okay, we will just we'll just come up with this value for now. Anyway, now the negative value wouldn't work because it need to fit this. Okay, so in this case, in part A, it needs to be positive. Well, anyway, the point is that you follow this simple formula to come up with the polar coordinate of any point on the plane. So please do example 7.10 as part of your homework. Next, we are going to plot the polar coordinates. Now, to plot this thing, we have to first have something called the polar graph paper, which you can download, or you can just take what the book has. See, right here, they have a nice little graph here, and then just use, and then just print this thing out. Maybe make a make a few copies of it and then print it out or something, or download something on the internet that looks better to you. Anyway, well, one page, and you can fit probably 6 of them in one page if you print it out, and that should be enough. Well, okay, maybe a couple pages. or you can draw it by hand, which is much less accurate. But in any case, this is for plotting it by hand. You should plot a couple of graphs by hand, even though we can plot everything in the Desmos graphing calculator. In fact, that's what we're going to do most of the time. However, remember to plot a couple of points at least to get a feel for it, so you know how it's done. And anyway, so to plot this thing, how are we going to plot a point? To show that point, let's look at some example. Let's see part. Example 7.11. You are going to plot, let's say we plot 7.11.a. This is on the following page. The way you plot a polar point is, I think I will just show it to you on a, let's say you are plotting 2, r equals to 2. This is example 7.11 part A. Okay, you're supposed to plot 2, pi over 4. So the r equals to 2. So what you're going to do is r means the radius. Okay, so you count the radius. Is this thing focusing? And anyway, you count the radius. You notice the first circle in the inside is 1, and the second circle is 2. Actually, I think I'll just draw it out. That might be better. Okay, r equals to 2. So we're plotting one point r equals to 2, where theta equals to pi over 4. So to plot this thing, r means radius. So you're going to draw a circle with radius 2. So that's radius 1 and radius 2. So the radius of this point is on 2, which means it is any of these things, anywhere on the second circle. Well, what you need next is what's the angle? The angle is pi over 4. So what's pi over 4? That's right about here, right? Something like that. So here's your point, right here. And that's how you plot any polar graph. Is first you figure out the radius, which is how far is a circle, the radius of the circle, how far it expands out from the middle. And then second, you need to figure out what the angle is. Okay, which way does it spin? It can be here, all the way down here, whatever. And then, and then notice, I should mention that sometimes the r is negative. Okay, you might r equals, as example B shows, r is actually negative. Now what? How do you do a negative angle? Well, let's look at example B. Okay, which you're supposed r is minus 3, and pi is the angle is 2 pi over 3. So being that r is, so the second point, r is minus 3, and pi is something, theta is 2 pi over 3. Now at this point, what you're going to do is minus 3 is still 3, so we'll draw the third circle where radius is 3. And then the angle is 2. Well, but what's minus 3 radius? Well, we'll wait a little bit. It's somewhere in here. And let's look at the circle, the angle. Angle is 2 pi over 3. What's 2 pi over 3? That's 2/3 of pi. That's somewhere in here. Okay. And then, so there's where the angle is. But being that r is negative, where normally if r wasn't negative, that would be the point, right? But being that r is negative, we're going to go the negative direction of r. That is the opposite direction. And locate the point to be down here instead. And which is also what your book says, right? So that's how you do a negative angle. Sorry, a negative r. A negative angle, you do it like any other way. Okay, you use the angle moves downwards. Normally the angle moves outwards for positive, and downwards if it's negative, just like in trigonometry. There's no difference here. And that's how you would plot this thing. So please do example 7.11 as part of your homework. So next example, let's look at example 7.12 on the following page, where it says we're going to graph something that's called r equals 4 sine theta. And how are you going to do that? Well, we are going to find a bunch of points, okay, and then do this trick one at a time. Preferably you have a graphics paper printed out, and then do this is much nicer than drawing it by hand. and probably unless you can draw nearly perfect circles in equal distance. Okay, this is 1, 2, 3, etc. But anyway, so to plot r equals to sine theta, and you're supposed to do it from theta to 2 pi. Therefore, you're going to calculate what these things are, right? Which gives you a nice chart, as the book shows. See, you come up with a chart like this. It's probably better if you use it, and it's easier to do this in some spreadsheet, probably. But, well, anyway, however you might do this. So you pick out a pile of points. How many points are here? What, like 15 or 20 or something? Anyway, you plot a pile of points, and you do this thing, and then you have you come to realize that this thing, the r equal to 4 sine theta happens to be a circle. And what's more, as you plot the points, then you'll soon realize that you're repeating it. You only have to do it from 0 to pi, because above that and beyond that, you're just repeating yourself. Okay, this thing is just going around and around, so you have drawn it twice. But in any case, it's good to plot this thing, I don't know, once or something, and then it looks like a circle. But can you prove that it's a circle? Yes, you can prove that it's a circle by manipulating the algebra. And then finally, that is, you solve for x and y, and sooner or later, you're going to realize that this thing is a circle. See? And towards the end of the example, you can see that, yeah, if you add this stuff up, very soon you recognize it to be a circle. Where x squared plus y minus 2 squared, x squared plus y squared equal to a positive constant is a circle. So that's that. All right, so that's why it becomes a circle, and that seems like a lot of work to plot some circle. But for my class, all you have to do is just do maybe a couple points, and then do the rest of the work, type it into the Desmos calculator, which is, I have the link down in below this video, where how to do polar, which website you use to do polar coordinates. And also to type in polar coordinates, of course, you have to type in theta. And to type in theta in the Desmos calculator, one way I found is just type these letters in, all 5, theta, theta. The second you type this in, it changes the Desmos automatically change this word into this letter. Very neat. I mean, it's one smart calculator. So then you can type this in, and that thing just draw it right out. Okay, and you can adjust it from 0 to theta to pi, or 0 to 2 pi, and see what it does. And you notice that there's no difference. 0 to pi, 0 to 2 pi is all the same. You just draw that circle there. And so please do example 7.12 as part of your homework. Now, especially if you're not a bit rusty or have never seen the polar coordinates, if there's nothing wrong with plotting the graph with a calculator, but remember to plot yourself a point or two on the graph. That way, it gives you a feel for it, and also double check to see if the calculator didn't screw up. Because if the point that you plot is nowhere near inside the graph, then somebody's wrong. Either you're wrong or you typed it in wrong. The calculator is unlikely to be wrong, but still possible. So at least for this section, always put, when you plot with a calculator, at least do a point or two yourself by hand, or at least in your head, to just double check things so that you know what's going on. Next, let's look at example 7.13 in the next page, where you're supposed to transform polar equation into rectangular coordinates. Well, that you just, based on this information you're given, and plug it backwards and do algebra. Okay, there's no calculus in that. And that this is you likely have done this in the past, but we'll do, I don't know, a thing or two of this kind just for the fun of it. So that's example 7.13, and please do that as part of your homework. Next, let's look at page 651, where there's a chart of various polar functions. that we can look at, or equations. For example, theta equal to constant is just a straight line. I'm looking at page 651. Okay, and so when theta is a constant, that means r can be anything if theta is fixed, which means straight line through the origin. Next, a circle is in the form of a cosine theta plus b sine theta. A and b is some number, I guess. And then, yeah, they'll draw you some kind of a circle. The spiral is where r equals a plus b theta. Well, it just works out that way. If you're welcome to make up some a and b numbers, like maybe a is 1, b is 2, and then, or maybe even, well, whatever. The point is, you can make up a number and plot this thing on the graphics in Desmos to see how it comes out. And that's a regular spiral. And next, this thing is called the cardioid. Whatever it's called, it looks kind of like an apple, I guess. And that you can draw. I'm looking at the following page. And next, the limison is similar, okay? It's similar to the cardioid because except there's a small loop in the middle. Next, the rose is just a four-petaled flower. It's called a rose. Probably should call it a clover or something. I don't know. Doesn't matter. It's you draw these things, okay? They're neat, and keep going. And then there's some other thing here. Well, whatever. There are various ways of various formulas can come up with various drawings. Some of them look pretty fancy. If you might want to try drawing some of them in the Desmos calculator. Remember, the longer the graph is, then the more you have to run the t, negative or positive. I don't know which. Okay, you just have to excuse me. Anyway, yeah, for something that goes in detail, what is that? Something like this thing here in your book. I don't know how much you have to run the t. You might have to run the t to 100 or something, from 0 to 100, or maybe minus 100 to 100. Maybe not quite 100. Anyway, you just make the t bigger and bigger until the whole graph is finished. Once it's finished, it probably will repeat itself, so you don't need to get any bigger than necessary. This kind of thing usually repeat itself. That is, as you, for example, like this graph that we look at, like this thing. Okay, what happens when you draw this thing when you increase t? It just repeats itself. It draws the graph once, up to maybe 2 pi or pi or something like that usually, and then it just keep going. Okay, if you increase the number, the graph doesn't look any different. That's because it just keep repeating itself and running through the same path. Well, except for the spiral, of course. The spiral doesn't repeat. The spiral will get bigger and bigger. It's a spiral. And so next page, we have how do we describe a spiral? Well, the spiral is defined as the distance equals to r equals to k theta. That is a spiral. You can, if you convert that into the rectangular coordinates, as we see where on page 654, if you turn that into a rectangular coordinates, plug it in, and things look like a headache. Okay, but in polar coordinates, things look very simple. For example, like here's a spiral here on the page. You notice that the equation of the spiral is r equal to k theta. Simple enough. But you would convert that information into the rectangular coordinate, suddenly you got tangent and square root and all kinds of stuff to look complicated. But actually, in the polar coordinates, it's just r equal to k theta. And which is one benefit of polar coordinates is that for certain functions, they're much simpler to handle than the rectangular coordinates. All right, so let's look at the next page. What is this? This is yet another kind of spiral where the spiral goes out fast, and I think it even has a name for it. Well, we'll worry about the name later. The point is, some spirals kind of winds around, gain slowly, whereas other kind of spirals gain faster. The reason it gains faster, well, is because there's a theta there. Okay, so for example, like r equals to, well, it doesn't matter. You can see that, okay? There are different kinds of spirals, and some grow quickly, kind of like the seashell that the book likes to talk about. And we don't care about, I mean, I don't care about seashells. Anyway, let's move on. Moving on to the symmetry properties of the spiral, because the angle and well, sometimes sine and cosine. For example, sine of a negative angle is negative of the sine of the angle, and cosine of the negative angle is just the angle cosine of the angle itself. As a result, things tend to be symmetrical and in different ways. For example, it can be symmetrical with respect to the x-axis. In polar coordinates, that's called the polar axis, doesn't matter. The point is, like this thing right here, what is that? Well, whatever it is symmetrical along the x-axis. And there are different reasons, I mean, different tricks to, or properties, how things are symmetrical. There's which the summary is written on page 656. That's mildly interesting, and please read that. That, yeah, or you, whether you read it or not, you're going to realize it as quickly if you do a few plots of these things, especially if you plot it by hand. Then you realize that sometimes something is just reflected along the x-axis, and sometimes it's reflected around the origin. That is symmetrical with respect to the origin. Either way, so stuff is symmetrical. This is on page 656. So please read the various ways that it can be symmetrical. Just get an idea. It doesn't really make much difference. You can plot it either way, whether it's symmetrical or not. So please read how things are symmetrical on page 656. Oh, I forgot to mention that you should also do example 7.14. It's just a quick description of the spiral in rectangular versus polar coordinates. In rectangular coordinates, it's just k times theta. Okay, in polar coordinates, it is a big long equation, which nevertheless can be derived right away. So please do example 7.14 as part of your homework. Next, let's look at example 7.15, where we are going to use symmetry to graph some polar equation. Yeah, actually that's for back in the good old days when we didn't have the Desmos graphics calculator. Now we're just going to, well, the symmetry is okay, and so please take a look at this example and what they're doing. Okay, because stuff is symmetrical, they can graph one part of the thing and then reflect it into the other parts so that you don't have to work so hard. That's the idea. Or we can just plug the whole thing into the calculator and draw all four parts, and we don't care which way the symmetry goes. Either way, so please do example 7.15 by just graphing it, putting it in the graphics calculator. However, take a quick look at what they're talking about when they say which ways the symmetry goes where. It's worth looking at. So please do example 7.15. So that's the end of this section. For homework, please do on page 660 problems 151, 157, 59, 61, 65, 69, 71, 75, 77, 81, and 83. Now, most of these problems are very, very short, being that I'm expecting you to graph this stuff on the graphics calculator. Again, the link of the calculator I have it at the bottom, in the video descriptions. Or you can even find your own, okay, if you prefer if there's a better one that you can find. In any case, so please type the stuff in and then and look at the different graphs, and remember, if you are not that familiar or have forgotten how the polar coordinates work, each time before you graph it on the calculator, pick a couple of representative points, 1 or 2 points to plot it by hand, and to double check the calculator to make sure that that something didn't go wrong. Yeah, I guess that's about it. Now, I'm not going to talk about the homework because you just type it into the calculator, and I haven't found it to be particularly worth mentioning. So, so that marks the end of this section. The only thing that's worth mentioning is when you graph it in the calculator, you have to type in theta to represent the Greek letter.